Well, welcome Woodland Park. This is Mr. Bergmann right here. I should change colors here. Mr. Bergmann here. And today we're going to start a new unit. Not too bad. We're talking about Chapter 17. We're going to talk about something called electrochemistry. Now, electrochemistry, of course, is chemistry with electrons, the chemistry of electrons. And when you think of electrons, you should also realize that electrons in motion. So if I have an electron and I move it, that creates something we, of course, call electricity. And so we're going to be studying, essentially, the chemistry of electricity. So this is very cool. Like, how does a battery work? What is a battery? How does all that work? We're going to be talking about that. And here is, of course, a list of objectives. The first thing we have to do is we have to understand, do a little review of oxidation reduction reactions. So that's going to take us a pretty piece of time. And then we're going to learn about these things, galvanic cells. You can see batteries are down here, electrolysis. That's a pretty cool concept, too. So let's kind of just dive into this and then see where it takes us. First of all, let's remember some things about oxidation number. So one thing, as you might realize, oxidation reduction reactions, remember, Leo goes grrr, gain electrons reduction, lose electrons oxidation. That is actually the heart and soul of how batteries work. So let's review how to oxidation numbers. Remember, if something, oxygen almost always has a -2 charge. So oxygen in HNO3 has a -2 charge. So O would be -2. That's his oxidation number. And then hydrogen is +1. And then that makes the nitrogen, you have to do algebra. You should say +1 plus X -6. And since there's no charge for nitric acid, we'd say that adds up to 0. So X looks like it has to be, the nitrogen has a charge or oxidation number of +5. For the lead sulfate, the lead, actually you'd probably know, sulfate has a charge of -2. So the lead is +2. The oxygen is -2. But then we've got the sulfur, and that'll have to be +6 because that has to add up to a total of, or is it 8? I think it's 6. We'd have to, let me do it again. So it's PbSO4. Let me get a blank screen to be easier to look at it. If you got PbSO4, that's +2 plus X -8. That's because O is a charge of -2, and there's 4 of them. And that adds up to 0. So X is +6. Yeah, so it is +6. Okay, and then the last one, this is a tricky one, NH42, NH42, CeSO43, so CeSO43. Now we just did sulfate up here, and so let's kind of break this out. Now if you kind of look at this 2 right here says the ammonium is +2. So actually if you think of it this way, NH4 is +1. We can work on him. And then sulfate has a charge of -2. So you could say CeSO43 has a charge of -2. Otherwise that's why this 2 is right here. So let's do the nitrogen. This will be X for the nitrogen +4 for the hydrogens. 4 times 1 is equal to +1. So that makes X has to be +5. Now the one that's tricky here is the cerium, Ce. The sulfur, we already just learned from up here, is +6. So I can say X plus, and now there's 3 of these, 18 minus is 12 times 2 is -24 is equal to -2. So what's X going to be? It's going to have to be, we need to get to 22, so it'd be 22, 4, right? 4 plus 18, yeah. So it'd be +4. So that's a review of oxidation numbers. If you remember how to do that, that's how you do this. Now let's balance some redox reactions. We've done these before. We do the half reaction method. And so remember, you want to have aluminum here, and that's going to go to Al +3. Notice that this is in an acidic medium. Another thing that you want to do is you want to get the electrons, to cancel. And so half reaction, notice how I started right here in the middle of the screen. And then the permanganate, MnO4-, and that's going to turn into Mn2+, plus 4 waters, because I got to get the 4 O's from over here, plus 8 hydrogens, and then we're going to have 5 electrons on this side, because if you add this up, this side is a charge of +7, and this is +7 here, and this is +2, so I need 5 electrons. Now I need to get the electrons to cancel. So to get the electrons to cancel, notice I have 3 electrons on this side and 5 electrons on this side. So this side will have to be multiplied by 5 and this one by 3. So I'm going to just kind of carry this through. Hopefully you can follow along. So that'll be 5 ALs plus, and this is 3. I'm going to take 3 here times 8, 24 hydrogens plus 3 permanganates, MnO4 negatives. Don't forget the charges. A lot of times people forget the charges. That'll mess you way up. Plus 5 aluminums, 3 positive, plus 3 Mn2 positive, plus 12 waters. There's nothing to cancel out except the electrons. This, of course, became 15 electrons here, and this became 15 electrons, and they canceled. Nothing else canceled. Sometimes you get the waters or the hydrogens or something to cancel. That is not the case in this particular reaction. Let's do another one here. Okay, this is another tricky and ugly one. So I've got Mg and MgOH. Now, this isn't a basic medium. So this first one, let me show you a shortcut. Mg goes to MgOH2. Now, we've learned that you can just add waters and hydrogens, but since this is hydroxide over here, I can just add 2 hydroxides to this side. And that balances, of course, except the electrons. The charge I'll need is 2 electrons on the product side there. And then we've got OCl minus, and that's going to turn into Cl minus. Now this one I'm going to play the water-hydrogen game. Plus 1 water. I get an O on this side right here, right there from that. That's the water. That's going to give me 2 hydrogens on this side. And now, of course, I've got the hydrogens. I'm going to add 2 hydroxides to both sides. And these became 2 waters, but there's already 1 water here, so this water goes away, and this just becomes a water. Now let's play the electron game. The charge on this side is -1. The charge on this side is -3, 2 here and 1 here. So I'm going to need 2 electrons on this side. Now, no, that's a cool one because the electrons already cancel, so we can simply add them up. Now, when we add them up, one thing good to note is the hydroxides cancel. And, yeah, that's it. So I'm going to get water plus magnesium plus OCl minus makes MgOH2 plus chloride. And that's the answer. Okay? And then there's a problem. This is, I call it the big nasty. If you could do the big nasty problem, you can practically do anything. This right here is a big nasty. First of all, I know it's an acidic medium because I've got sulfuric acid as one of the reactants. And so I need to find the 2 chemicals. Remember, one thing must go up and one thing must go down. And so I'm looking to see which ones go up and which ones go down. And so if you look here, the manganese, it looks like he's doing some changing. Probably this is just your acid piece. So probably this guy is going to change, and so is the manganese. And so the half reactions are going to get, frankly, kind of ugly. This is going to be a long one. I'm going to create a new screen. I'll probably have to switch back and forth a few times. So I'm going to do the K4 one. So I've got K4. Let me find it, sorry. K4, FeCN6. Okay. Fe, parentheses, CN6. And that's going to turn into a whole bunch of other things. The iron, I've got to balance, remember, everything but the hydrogens and all that. And, all right, I'm going to balance it with the irons. I'm going to put FeSO4 on this side. So FeSO4. Was it Fe2SO4? Yeah, it is. Okay. So that's going to be my irons. I'm going to need the carbons and the nitrogens taken care of. So the carbons are here, and the nitrogens are in the nitric acid. So I'll know nitric acid and carbon dioxide. So HNO3 plus CO2. Good. And I need the potassium. Here's the potassium. So I'm going to put the KHSO4 on this side too. Now let's begin balancing. Let's balance everything. Now I've got 2 irons on this side, so this is going to require a 2 right here. All right, that's going to give me 8 potassiums, so I'm going to need 8 of these. Good. Now you do the hydrogens, oxygens at the end, and we'll do that. Now how many carbons do I have here? I've got 6 times 1 times 2 is 12 carbons, so I'm going to need 12 carbon dioxides. And then the nitrogens, I've got 12 nitrogens, so I'm going to need 12 nitric acids. Now how's that for ugly? Okay. Now what we need to do is do our hydrogens and then our oxygens. Do our oxygens first. There's no oxygen on this side, so I'm going to have to say plus water on this side. And I need to count up the oxygens. There's a lot. Here I have 12 oxygens. Here I have 12 times 2, I got 12. And then from the iron compound. And then I have 12 times 3 is 36 oxygens from the nitric acid here. From the carbon dioxide, I have 24 oxygens. And then from the potassium hydrogen sulfate, I have 32 oxygens. That adds up to 10, 11, 12, 14, 3, 4, 5, 6, 7, 8, 9, 10. 104. So we're going to need 104 waters. Oh my word, that's a big number. Now what else have I not balanced? The hydrogens. So I'm going to have to put some hydrogen on this side, but I do already have some hydrogens. The hydrogen count on this side looks like we've got 12 from the nitric acid, and from the here I have an additional 8. So that adds up to 20. So if I subtract 20 from 104, I get 84. So I need 84 hydrogen ions. Now let's balance the charges. The charge on this side is 0. There's no charge. The charge on this side, actually, if you look at it carefully, everything's got a 0 charge except for the hydrogens, is 84 positive. So this will be plus 84 electrons. Okay, that's just the first half reaction. Probably we need to sort of neatify that. So let me do that. So I've got 2K4 Fe CN6 plus however many waters. What was the waters? It was a big, no, 100 and something. 104 waters. And that's going to make Fe2SO43. Kind of trying to write it small here. Plus 12 carbon dioxides. Plus 12, what was it, nitric acid. Plus 8 KHSO4s. Plus 84, I'm going to put that over here, plus 84 hydrogens, plus 84 electrons. Oh, that was just a half reaction. Well, imagine the other half reaction. Actually, it's not as bad. Now, the other thing I have not done as a change is I've got KMNO4 right here, and that's going to turn into MnSO4. So KMNO4, so I'm going to have KMNO4 turning into Mn, what was it going into? SO4. Now, there was also sulfuric acid, and that was on this side of the reaction, right? Yeah, so I'm going to add H2SO4 on this side. Now we've got all the pieces and the parts, so let's now start the balancing in here. Oh, I also have to say plus KHSO4 because I've got that K problem. That's okay, that's not too bad. So I've got 1 potassium and 1 potassium, so that's good. My manganese, I got 1 and 1. I'm happy about that. My sulfates, all right, now I'm going to have to put a 2 here because I've got a sulfate here and a sulfate here, and so that gives me a 2 sulfates on this side. Now let's count our O's. I've got, actually, yeah. I've got, if I count sulfates, that takes care of all my oxygens, but I still have these 4 oxygens, so I'm going to need to add 4 waters on this side. And now let's count up our hydrogens now. I've got 4 times 2 is 8 hydrogens, plus 1 is 9. So I've got 9 hydrogens on this side. And on this side, I have simply got 4. So I'm going to need 5 more hydrogens. Good. Now charge-wise, the charge on this side is 0. Charge on this, I'm going to need 5 electrons here. Unfortunately, you might realize this, but 84 and 5 are not multiples of each other. And so we're going to have to multiply the top one by 5 and the bottom one by 84. So this probably is sufficient to do a rewrite. So I have no idea. When we multiply by 5, first one I can do, I can say 10K4 FE CN6 plus 104 times 5 is a lot. 104 times 5 gives you 520 waters. That's a big coefficient, isn't it? Plus, these we're going to multiply 84. 84 times 2 is 168. 168 H2SO4s plus 84 KMNO4s. I believe that's the full products or reactants. And the products, I'm going to say 5 Fe2SO43. Notice I gave you a full page for this one. Plus, total if I had that 60 carbon dioxides plus 60 HNO3s plus, all right, 84 times 5, I don't know what that is. 84 times 5, hydrogens is 420. 420 hydrogens. That's this hydrogen right here. Now I'm going to do this one. 8 times 5 is 40 plus 40 KHSO4s plus, now let's do this, 5 MnSO4s plus 5 KHSO4s, O4s, plus 20 waters, H2O. Now, I think we got a couple of common factors on either side of the equation. And the arrow's right here, right? And so I've got 520 waters here, and what did I say, 20 waters here? 20 here. So that's going to be 500. This number just becomes 500 waters. These go away. I think I got a hydrogen. I got hydrogens here. Oh, you know, I forgot the hydrogens on this side, didn't I? 5 times 84, right? Or did I already do that? Okay, hold on. I've lost my place here. Yeah, I need that. 84 times 5 gives me 420 hydrogens. Where do they go? You know what? These 420 hydrogens need to be on the other side. They're a reactant. Okay? But I believe that's it, unless I've got some combinations. Oh, I got KHSO4 here and here, so that's the same thing. So I can just 40 plus 5. So there's your answer. How ugly is that? Whew. If you can do that, you're really good. You've got it all figured out. So now let's talk about this. Okay, now electrochemistry. So just review. Because you see we have to remember how to do oxidation reduction reactions because they are the ones that cause all these things to occur. So let's talk about something called galvanic cells. Galvanic cells were invented by a guy by the name of Galvani. He was an Italian guy, and he talked Italian probably, since he was from Italy. Duh. And he was the one who first basically built the first battery. Okay, oxidation, as you recall, you lose electrons, or you gain charge. It says charge, not gauge. And reduction is you gain electrons, or you lose charge. And you know that I like to look at the charge because reduction sounds like you're losing something and you're losing a charge. So how do you make something called a galvanic cell? And essentially a galvanic cell is a battery. If you understand, basically we're trying to understand how does somebody make a battery. It is really quite fascinating how batteries are made. Here is the deal. You essentially make a separate container for each half reaction. So usually what we do is if we wanted to make a oxidation reduction reaction, we'd pour the chemicals into one container and then boom, the reaction would occur. But in the case below, what you do is you take the chemicals and you put them in two separate beakers and then you separate them by a wire. Because you see, since electrons are going to be moving, I'll change the color. When the electrons are moving, if you cause them to move through a wire, boom, like such, well, you could put a light bulb between there and it'll turn on. Now, we do have an issue with this particular cell. One thing that's true about this is a cell is this kind of all connected. You need something we call a salt bridge. Without the salt bridge, you can't have this occur. It's, I don't know if you understand much about electricity, but you need a complete circuit. If there's a break in a wire or in a particular electrical situation, it's not going to work. So we need to add a little container here filled with a liquid, and that's what we call a salt bridge. And without the salt bridge, this reaction will not take place. So if you look at the next picture on your screen, here's the deal. There's two kinds of salt bridges. By the way, if you put a salt bridge, it will produce a current, electrical current. An electrical current, by the way, is electrons moving for a long time. And you can see there's two different varieties of salt bridges. You can see in example number 1, we have what we call the U-tube variety. Whoa. And if you have this one, we have a porous disc that exists between the two containers. And again, if you put a light bulb right here or right here, it would light up the light bulb and you would get you'd turn the light bulb on, depending on whatever. And so this is how we can do this. So we put a colute solution into beaker 1 and beaker 2. So this will be the reduction one, or this will be the oxidation one. Or it could be vice versa. It makes no difference. You're going to get a chemical reaction take place. Let's take a look at a more involved picture, or just this zoomed in. Now, let's learn some terms. There's some very important terms that we're going to use. Actually, I think I won't go to the blank screen just yet. This is a galvanic cell right here. And in this galvanic cell, the substance that is the reducing agent is going to send electrons through here, and then the oxidizing agent is going to lose electrons into the solution. Now, here's something that you must know, all right? Oxidation, write this down, occurs at the anode, and reduction occurs at the cathode. Now, the way I've remembered this over time is oxidation and anode are both vowels. Vowels? How do I spell? Vowels, okay. And R, reduction occurs at the cathode, are both consonants. So keep your consonants and your vowels together, and you're a happy camper. So that's something that's important. And so if you notice here, this is the anode, and the reducing agent, if you recall, is the thing that's being oxidized. Oxidation occurs at the anode. Reduction occurs at the cathode. Now, cathodes in a galvanic cell are positive. You ever looked at a battery, and you look at a battery, they got a positive and a negative sign. Well, the positive sign has to do with the cathode. The positive will be the cathode, and the anode will be the negative. And if you remember, cations are positive and anions are negative. That's a way to remember that. Or you might remember that cats are good, or some kind of a mnemonic device that will help you to remember these things. And then we'll label one in just a minute. But another picture that you've got in your notes is you can see this would be a galvanic cell, and then you could measure voltages. Okay, very cool. And yeah, I'm going to label the parts in a second. By the way, if you do not have actually, let's label the parts. I'm going to create a blank screen to do this. So let's say I have a reaction. The classic galvanic cell is actually this reaction right here. If I take Cu2 positive, and it goes to Cu plus 2 electrons on this side, and then I have zinc going up to zinc plus 2 electrons. When we add these reactions together, you simply get copper 2 positive plus zinc makes zinc 2 positive plus copper. Now, the copper is reducing and the zinc is oxidizing because, of course, the copper is gaining electrons, or I like to think his charge is going down, so he's reducing. And the zinc is oxidizing, his charge is going up. So we can make a battery out of this. Now, I could just throw these chemicals into one big beaker and make it work, but you're not going to make a battery. So if you want to make a battery, what you need to do is have 2 containers. You want to sketch this, and we'll make some batteries, so lots of batteries in class, actually. let's put a salt bridge in there, and let's make 2 containers. They're supposed to be outside. And on this side, let's take and let's put some copper 2 positive. Probably you'll dissociate with, let's say, copper chloride or something like that. And into this, you're going to place a piece of copper. So I'll color it, copper colored. So that there is a strip of copper. Okay. And on this side, I'm going to place some zinc +2. Let's say chloride again. The chloride won't make a difference. And into that, I'm going to place a strip of zinc. And then between that, I'm going to put a voltmeter, which will symbolize with a V. And this is a wire right here. This black line right here is a wire. Now, we would like to ask a number of questions. There'd be a porous disc right here. Lots of questions. Who's the cathode? Who's the anode? First of all, let's label the cathode first. Oxidation occurs at the anode. Who's oxidizing? Well, the zinc is going from zinc to zinc 2 positive. Sometimes it's wise to write the reaction, down here. And in that reaction, if you recall, we have the Cu2 positive plus zinc is going to zinc 2 positive plus copper. And so the zinc is going up in charge from 0 to +2. So he's going up. Up is oxidation. So that makes this cell right here, this portion, this is called the anode. And this would have a negative charge. Conversely, this is the cathode, and it would have a positive charge. Actually, technically, the piece of metal is the cathode, and the piece of zinc or whatever the piece of metal is the anode. Now, the question they're going to ask is, what is the direction of electron flow? What direction do the electrons flow? Now, if you think about it for a moment, we actually wrote that in our previous example here. The electrons are going to leave the zinc and go into the copper. So the electrons are going to flow this direction, you see, because they're leaving the zinc. Now, you might just remember they essentially flow from the anode to the cathode. That would help as well. The other question that's going to be asked is, what is the direction of the ion flow? What is the ion flow direction? Well, since this side is becoming more and more negative because electrons have a negative charge, what's going to have to flow across here are going to be cations. The zinc, and this is called a salt bridge. Oftentimes in the salt you'll say take some sodium nitrate, and then what's going to happen is the sodiums are going to flow through here, but that's going to make this side, because what you want to do is balance the charge. If this side is more negative, you're going to put some cations in there with a positive charge, and then conversely anions are going to flow in here. Essentially the chlorides, these chlorides, and maybe some nitrates are going to flow in there. And those are the things that they're going to label in a galvanic cell. And folks, you could put a light bulb in there if the current's high enough, and you could make a battery. Now, I want you all to notice in this particular diagram that I put the copper metal in the copper solution and the zinc metal in the zinc solution. But what would you do if the reaction did not have a metal? Sometimes the reaction that's taking place is a gas. And so here's an example here. What happens when one of the electrodes is not a metal? Well, this one we have a zinc system right here. So they put a piece of zinc metal in here. But in this particular half reaction, it's making hydrogen gas. And so they're going to use a tube filled with this. And then the most common electrode that's used is a piece of platinum. And platinum doesn't like to react, so it's a perfect one. And you can actually collect the gas. So you may sometimes, notice here's my voltmeter, and apparently it's 0.76 volts. All right. Now this is a good picture. This is the one I just drew for you, although it looks like it's in reverse. They use sulfate here instead of chloride, but it would give you the same too, and the voltage here would be 1 volt. But I want you to notice what's going to happen. What's going to happen to the copper over time is the copper is going to become thicker, because as you recall, the copper 2 positive is turning into copper metal. And so as time goes on, the piece of copper, if this is the copper over here, sticking in, it's going to start getting thicker, because copper is going to be deposited. You can plate them. One thing cool about this is you'll plate copper onto the metal. In fact, you could actually use any piece of metal you'd like. You could take a piece of iron in there, whatever, and then the copper will become copper-coated. Now, on the reverse side, the zinc, though, if you recall, the zinc is turning into zinc 2 positive, so it's ionizing, and so it's breaking apart. So if I were to look at the zinc here and then look at it later, it's going to be etched and smaller. So the zinc is going to get lighter in terms of weight, and then the copper is going to become heavier as the battery proceeds. Okay? Now, this can be summarized, and this table right here is the most important table that there is in all of Chapter 17. It is called the Standard Reduction Potentials Table. I don't recollect which particular page this is on in your book, but it is critical. This diagram is the critical diagram. Let me zoom in on it for you. You can see this. Now, let me give you a couple of hints about this. This gives you half reactions. Okay, first of all, these are all half reactions, and these are standard reduction potentials. Now, notice they are reduction potentials, so it assumes that all reactions reduce. Now, that's not true. Many reactions will oxidize, and so if you wanted the oxidation, you would just flip it. So if I wanted to take this reaction, the lithium reaction, and if I were to lithium goes to lithium positive plus an electrons, then actually his, and we'll talk about this, is the E0, that's the voltages. The voltage will be positive 3.05. So if you flip a reaction, reverse it and make an oxidation reaction, then the sign simply changes. Now let me also show you some interesting things. You know, you've been learning on oxidation reduction reactions how to do balanced reactions, and I've taught you how to do this. Mr. Sams has taught you. We've done it podcasting. Do you realize that this table is a list of all of the half reactions that are pertinent? There are more than this, of course, but almost every half reaction we've ever done has come from this table. So instead of you having to work the problem out, like the permanganate one or whatever that we just did a little bit ago, this one right here, we did as an example, this permanganate reaction is already written for you. You can just copy it from the book. Will you have this book, this table on the exam, the AP exam? You bet. Will you have it on the Chapter 17 exam? You bet. This table is always available. Now, we've got a new thing we haven't learned about. That's called the electrical potential. The potential, it's a voltage. And it's, if you study electricity, we're not going to get into too many details, but it's the voltage. You've probably heard of voltages and stuff like that. You have a 9-volt battery or something like that, and this kind of gets us that. Okay, so this table assumes, first of all, so let's begin to use this table. It assumes a couple of things, that you have a 1.0 molar solution at 1 atmosphere and 25 degrees Celsius. It's basically a standard conditions. But the standard is 25 degrees Celsius. And the other thing you have to assume is that you have a solution that is 1 mole per liter. Now, you won't always, and we'll talk about that in a little bit, okay? Now, let's see if we can figure out what would be the electrical potential for this reaction, okay? So essentially what we've got is we got PbO2 turning into Pb2 positive, and we've got Na going to Na positive. Guess what I'm going to do? It didn't ask me to balance it, but I want to go find from my table PbO2 to Pb2 positive. So we want to look on our table here, PbO2. I haven't found it yet. I'm looking. You might find it before me. There it is. Here it is. PbO2 goes to Pb2 positive. That's 1.46 volts. So I'm going to write 1.46 volts. And if I wanted to write the reaction, it was given in that problem, and you could go back. Now, the sodium will be easy to find because I bet it's right down here. Now, it's the reverse of this reaction. So it's this reaction reverse, and it's 2.71. So it'll be positive 2.71. And you know what you do? Volts, you simply just add them. So that's 6 and 1 is 7. 7 and 4 is 11. So it's 4.17 volts. So this particular reaction. Now, one thing to note here is that when you add the reactions, you know, if you end up with, you know, 2 electrons on this side and 3 electrons on this side or whatever, you'd multiply by 2 and 3. Do you multiply the voltages? No, you don't. Do not. You just add them. And it doesn't. It's not. These aren't like delta H's, which double or triple or something like that. They just are. So why that is, it just is. Let's do a couple more here. What if I want to go this? Now notice what I'm doing is I'm breaking apart into half reactions. Fe3 positive goes to Fe2 positive. So let's go back on our table and find 3 to 2. Fe3 to Fe2. I'm thinking it's over here somewhere. And I could also be wrong. Here it is right here. Fe3 positive goes to Fe2 positive. Looks like that's 0.77 volts. By the way, if the voltages are negative, then the reaction won't happen. If it's positive, they will. Mg goes to Mg2 positive. I'm pretty sure that's a pretty high positive one because that's going to be one of these down here. Mg to Mg2 positive, that's that reaction reverse. That's 2.37 volts. So positive 2.37. It was negative, and then we simply add them. 7 and 7 is 14. So 7, 10, 11. So 3.14 volts. So that's not terribly difficult. Again, if you end up with a negative number, then that reaction will not occur. So if you really think, if we were to make this reaction in reverse, it would not occur. We would say it's not spontaneous. Now, here's a couple of interesting examples we want to spend some time talking about. Is hydrogen capable of reducing silver? Basically what we want to do is, when they're asking these questions, hold on while I catch that phone. When they ask these questions, what they're essentially asking is the voltage positive? If it's positive, question mark. If it's positive, then it will occur. If it won't, it isn't. So Ag positive, if it's going to reduce, it can only reduce to just regular silver. So what is the voltage of Ag positive to Ag? So I go back to my table here. Silver, silver, silver. He's right here. Ag positive to Ag, that's 0.80 volts. So that's 0.80 volts. And then I have hydrogen, and it's going to turn into what? We go back. And actually, hydrogen, we should talk about that, is considered essentially the standard because the hydrogen is the 0 voltage here. So you can actually go either direction. It's 0 volts. That's kind of how the basis of the system is it starts at a 0, and it's the hydrogen deal here. So this is 0 volts. So does that add up? That adds up to 0.80 volts. So yes, it is possible because I got a positive answer. This is positive 80. 0.80 actually. Is it capable of reducing nickel? So we have H2, which we just learned just is 0 volts. If I want to reduce the nickel, Ni positive 2, down to nickel, let's go look it up on our table. So we find nickel, and I believe he's going to be up over here somewhere. Mine's getting all marked up here. It's negative 0.23 volts. Do you see that right there? So that's going to be negative 23 volts. Negative 0.23 volts. The answer is negative 0.23 volts. And of course, the answer is no because this answer is negative. So it's essentially just asking sort of some negative. All right, is iron 2 capable of reducing VO2 positive? So iron plus 2, and we have VO2 positive 1. Now let's go find the VO2. I want to reduce the VO2, and I believe he's somewhere up here. So let's see where the VO2 is. That's not a very common thing, but it is on the oxidation reduction table. I still don't see it. You might see it before me. Here it is. We have VO2, and that looks like it's a 1 volter. So this is 1 volt. Now he's going to be reduced. So that means he has to be oxidized. That means he has to go to Fe3 positive. And to go to Fe3 positive, Fe2 to Fe3 is this one. See that? But it's 2 to 3, so this is not 0.77, but it's going to be negative 0.76, negative 0.77 volts. And if we add that, that'll be positive 0.23 volts. It's positive, so the answer to that one is yes. So you see, we're just trying to find positive voltages. All right, is Fe2 capable of reducing Cr3 positive? Well, we just did this one, Fe2 to Fe3. I can do that. Remember, that was negative 0.77 volts. We don't have to look that one up again. But I want to reduce the chromium probably down to chromium metal. Cr is no charge. So if I go back and find the chromium, all right, looks like that's going to be positive. I want to reduce it, right? No, negative 0.73 volts. Negative 0.73 volts. That comes out to negative 0.03 volts. Now that's close, but negative is negative, so the answer is no. You get the idea? Now one more, and then I'll be done. Kind of a long podcast here, almost 40 minutes. Okay, rank the following from strongest oxidizing agent to weakest oxidizing agent. Now when you use the word agent, remember, basically we're talking about things that reduce. So we have to write the reduction reactions, and then what we want to do, this is a typo, Ce4 positive, right there, positive 4. And so what we want to do is write out the reactions where they reduce, okay? And then we're going to just write down the numbers. So Ce4 positive is going to go to what? So I have to go back to my table. So cerium, I think, is at the top of the list up here. Ce, I'm looking for it. Here we go. Ce4 drops to Ce3, and that's 1.7 volts to Ce3 positive. That's going to be positive 1.7 volts. That's a pretty good number. Okay. Now, can the Ce3 positive, if he's going to reduce, can he reduce any more? Do we have any Ce3 positive? So I'm now back on the table looking carefully for the additional cerium, and it's not there at all. I think all we get is that. So he's not going to be a very good reducer. He could reduce down to regular cerium, but if he's not on our table, then we're going to kind of eliminate him. I don't see him. We'll go find somebody else. So I'm going to put a question mark, so probably really bad there. Fe2 positive can reduce to Fe, and Fe3 positive can reduce to Fe. Let's see what these two numbers are back on our table. Fe2 positive, all right, here's the one I just found. Fe3 to Fe0 is negative 0.36. So this is negative 0.36 volts. The iron 2, though, iron 2, there it is right there, negative 0.44 volts. And you see that's what we're doing. So now I want to do magnesium 2, magnesium plus 2. That can go to magnesium. Now that's going to be really bad. Magnesium's an active metal, so he's going to be down in here. He's negative 2.37 volts. Negative 2.37 volts, negative. Now the nickel, actually on the magnesium, by the way, he can't reduce at all. He's as low as he can get, so he's kind of like the cerium. So we won't consider him. And then we've got nickel 2 and tin. So if I have nickel 2, nickel plus 2, that can go to nickel. And I go back and look at that one. And so I find nickel here. Nickel, nickel, where are you, Mr. Nickel? Hello, Mr. Nickel, where are you? All right, I can't find him. You probably found him before I did. You see, the table is hard to read. You probably should be looking at your paper as you do this, and I've still found Mr. Nickel. Nickel, there he is. 0.23 on the negative side. All right, so he's negative 0.23. And then we have 10. Well, 10 really can't be reduced anymore. There's no 10 minus da-da-da. No. So we can ignore them. So the ones that are already in their lowest oxidation state cannot be reduced. You could classify them together. And so basically we're going from, I don't know, highest to lowest. Strongest reducer, or strongest oxidizing agent. So the strongest reducer, we can just rank them. So number 1 would be this one right here, right? Because he's positive. And this will be 2. Now, what was my cerium one, or my negative 0.23? Actually, this is number 3, isn't it? You're looking at it all on one page, and I've got, this is 2 right here. And this is 4, and this is 5. So that's how you do that. Well, that concludes today's podcast. I hope you guys are enjoying AP Chemland. AP Chemistry is what? Well, it's fun. Ho ho! We'll see you in class. Bye.